this video, we're going to prove one of the results from the previous lecture. So the result is that for all proper initial segments of a well-formed formula, the number of left brackets is strictly larger than the number of right brackets. The first thing we're going to do is just reminder. Proper initial segment is a contiguous substring of a well-formed formula which starts at the beginning of the formula and is not the formula itself. So what I mean by this is, as an example, suppose that our formula were open brackets P1 and P2. A proper initial segment of this is, suppose I just do P1 and P2 and I don't close the bracket. This is a proper initial segment. So the result is, for any proper initial segment, the number of left brackets is strictly larger, which we can see in this example. We're going to do this by structural induction. So first, let L of, let's say, alpha equal number of left brackets in alpha. And similarly, we'll let R equal the number of right brackets. Okay, now, in the base case, we're going to say let alpha equal pi. So this means that this is one of our propositional variables, okay? Meaning alpha is in the core set. Then alpha has no proper initial segments. Okay, and if alpha has no proper initial segments, so the statement is vacuously true. Now, the inductive hypothesis will be, suppose that for all or what we want to do is suppose that the property holds for alpha and beta. Then we want to prove it for alpha and beta, alpha or beta, not alpha and alpha right arrow beta. Okay? Now, we'll do case, we'll do alpha and beta. Now, okay. Well, the first case can be, so let's let um, gamma be a proper initial segment of this well-formed formula. Then, and actually, like, you can sort of handle multiple cases at once if we sort of give this, as you can see, I changed this and to a star. So this handles basically all of the binary um, connectives. Now, you could have that gamma equals open brackets. So we'll say case gamma equals open bracket. Okay. And if this is the case, then property holds because there's one open bracket and no closing brackets. Okay. Now case gamma equals open bracket, and then let's say alpha prime. Okay. Where alpha prime is a segment, or let's say an initial segment of alpha, then L of gamma, which is the number of open brackets, equals 1 plus L of alpha prime. And we know that alpha prime, L of alpha prime, is greater than or equal to R of alpha prime. And if you think about why we know this, then if if alpha prime is a proper initial segment, then by the inductive hypothesis, we're assuming that the number of left brackets is strictly larger. But if it's not proper, meaning that alpha prime is actually all of alpha, then we have that the number of left brackets is equal to the number of right brackets. Okay? So that's why this holds. Thus, L of gamma strictly greater than R of gamma. And just to be a little bit more precise, we can say we also have that R of gamma equals R of alpha prime. And this is why. This is what justifies the fact that it's strictly larger. Okay. Now, another case can be, let's suppose gamma equals open bracket alpha prime, or no, all of alpha, and then whatever the connective was, and you stop here. Then, similar to the previous case. Okay? Yeah, the connective does not add a left bracket or a right bracket, so you can handle it similarly. Now, the next case is if gamma equals open bracket alpha star beta prime, where beta prime is a proper initial segment of beta. And what this means is it's basically going to be the same process as the second case. So up to open bracket alpha star, we have one more left bracket, then right bracket, and in beta we have L of beta greater than or equal to R of beta prime for both of these. So the property holds. Now, you can do this more formally, as we did in case 2, but because I already did it, I will leave it like this. Now, final case. Gamma equals alpha star beta close bracket. Oh, and in the previous case, this should not say proper initial segment. This is just an initial segment, so it could be all of beta. And this property holds because this is a well-formed formula. So, oh, and here we actually don't have to check it. Actually, I realize this case is unnecessary because we're assuming it's a proper initial segment. So this is not a case. Yeah. Oh, and in the previous case, there should not be a close bracket here. So this proves the result. This proves the result for the case gamma equals, or the case open bracket, some proposition alpha, and then some binary connective, and then another proposition beta in close bracket. Now for open bracket not alpha, close bracket, it's a similar process. So I will skip the similar cases. So case, we'll say gamma equals open bracket, similar case gamma equals open bracket not, and this works just by one left bracket, no right bracket, case gamma equals open bracket not, and then alpha prime for some proper initial segment. Oh, I keep writing proper, should be initial segment, alpha prime of alpha. And in this case, we say it is the same as open bracket alpha prime case in the previous case, or in the case of alpha star beta. So what I mean by this is, like, this is the exact same, like, the not will not affect this. You write the exact same argument as was done in this case. And yeah, this ends the proof.